Okay, so we are on the third part. We are still exploring the Nernst equation and we are focusing more on non-standard conditions. Okay, so let's look at this problem here. Consider the following galvanic cell at 25 degrees Celsius. So you are given the cell notation. Obviously, chromium 2 plus is oxidized to chromium 3 plus, while cobalt 2 plus is reduced to cobalt. And the overall reaction and equilibrium constant value are given. So that makes our life easier because the K value is already given with 10 to the 7th. We are asked to calculate the cell potential for this galvanic cell and the delta G for the cell reaction at these conditions. Okay, so remember that from the Nernst equation, E is equal to E naught minus 0.0592 over N log of Q. Okay, so that means we should need an E naught value. Okay, if this is the only thing given to us, we don't have to worry. Why? Because we have the K value, which means we can compute for our E naught. Remember, E naught at equilibrium, our E becomes 0. So our E naught becomes what? 0.0592 over N log of K. We already have the K value. Now, the tricky part here is to take note of the number of moles of electrons. So we should be able to, deduce from the reaction. This is our oxidation. That's one electron involved because it's changing 2 plus to plus 3, while this one here is cobalt 2 plus 2 electrons reduced to cobalt, right? So that means 2 electrons are involved. So that's fairly easy. E naught is equal to 0.0592 over 2 log of the value K, which is 2.79 times 10 to the positive 7. So let's see what's the E naught value here. Okay, let me just work out a calculator here. 2.79 raised to the 7th, taking the logarithm of that number, that's 7 point something, times 0.0592 divided by 2. It gives me an E naught of positive 0.220 volts. Okay, so let me just check that again. 2.79 exponent 7. Okay, we take the logarithm of that number times 0.0592 divided by 2. Yes, that's the small value, 0.22 volts. Now that we have the E naught value, okay, and look at these conditions here, definitely non-standard. We have a Q value, so we can compute for the E value. Okay, so the non-standard cell potential value, E, is equal to E naught minus 0.0592 over 2 in our case, log of, look at the reaction, product side, that's chromium 3 plus concentration squared, over our reactant side, we have concentration of Cr2 plus squared over the concentration of our cobalt 2 plus. So we just have to substitute that here. So that would be 0.220 volts minus 0.0592 over 2 log of, what's the numerator? Chromium 3 plus is 0.3 squared over chromium 2 plus is, where is that? Oh, sorry. Let me change that. Chromium 3 plus is 2 molar. So that's 2 molar squared. Chromium 2 plus is 0.3, also squared. cobalt 2 plus is 0.2. So let's look at the value of Q. How big is our Q? So that's 4 divided by 0.3 squared divided by 0.2. So that's a large value here. Logarithm of 222.222. So this quantity here is positive, which makes the second term negative. So our E will now be less than E naught, right? So just to connect with what we did in the previous video. So let's look at the value again. So that's 222. The logarithm of that times 0.0592 divided by 2. It's practically 0.22 volts minus 0.069. So RE, okay, plus 0.22 volts is even smaller. As we have said, it will be doing less work. So RE is still positive but smaller. It's 0.151 because our Q here is greater than 1. So that means we have a smaller quantity of electrical work that can be derived from our cell. Okay, so these are just some of the things that we have learned from the previous video. So let's just finish the problem. Okay, so what do we have here? We have already calculated for the E. So that means under these conditions, with this set of concentrations, we can derive less work compared with the standard condition, because the standard condition would have an E naught of 0.22 volts, while under this set of concentrations, we only ended up with 0.151. Now, we still have one more to work with, the value of the delta G. Remember, delta G is equal to what? Negative NFE. So that's the quickest route. Since we already have a value of the E from our previous calculation, we can now compute for the delta G directly. So that would be negative, again, that's 2 moles of electrons times 96,485 coulombs per mole, right, with 0.151 volts. Remember, coulomb volt gives you joules. So our delta G here, which is per mole of reaction, so that would be 2 times 96,485 times 0.151. It gives us negative 29,138.47 joules per mole, or negative 29.1 kilojoules per mole. See, delta G is still negative, so the reaction will still be happening, except that we can derive a very small quantity of work from there. Okay, so that's negative 29.1 kilojoules per mole. So this is an exploration of the equations that we have used so far and have been introduced to. Okay, so in the next discussions that we need to do, we will be exploring a little bit more of the concentrations as we go along. So as your assignment, okay, so this part here will be attached as an assignment. You have to repeat the entire procedure. Okay, I'm just showing you this so that you can work on it in your own time. But at the end of our discussion for today, you will just be asked a few questions, okay, on an online quiz with an application of what we have discussed at this point. Okay, so that is wrapping up our discussion of the Nernst equation. So this is the end of our third video.